In the ever-evolving world of aviation, a new player has emerged that's turning heads and challenging conventional notions of air travel. The Airlander 10, often humorously referred to as the flying bum, due to its distinctive shape, represents a bold step forward in aircraft design. This massive airship combines elements of blimps, helicopters, and airplanes to create a unique and potentially game-changing vehicle. Let's dive into the science, technology, and potential applications of this remarkable aircraft. The basics of the Airlander 10. The Airlander 10 is currently the world's largest aircraft, measuring an impressive 92 meters long, 26 meters tall, and 43.5 meters wide. Despite its enormous size, it's designed to be a fuel-efficient and versatile platform for various applications, from passenger travel to cargo transport and scientific research. What sets the Airlander 10 apart is its hybrid nature. It doesn't rely solely on one method of achieving flight, but instead combines three distinct technologies: buoyancy like a blimp, vertical thrust like a helicopter, aerodynamic lift like an airplane. This unique combination allows the Airlander 10 to overcome limitations of each individual method while capitalizing on their strengths. The science behind the flight. To understand how the Airlander 10 works, we need to explore each of its flight mechanisms in detail. Buoyancy, floating like a blimp. The primary flight mechanism of the Airlander 10 is buoyancy, the same principle that keeps ships afloat on water. In the case of airships, the fluid is air rather than water, but the physics remain the same. The key to achieving buoyancy in air is to create a structure that is, on average, less dense than the surrounding air. The Airlander 10 accomplishes this by filling much of its volume with helium, a gas significantly lighter than air. This allows the massive vehicle to float effortlessly. Much like a balloon, helium is chosen over hydrogen, which is even lighter, due to safety concerns. Unlike hydrogen, helium is inert and non-flammable, eliminating the risk of disasters like the infamous Hindenburg incident. The use of buoyancy as the primary lift mechanism offers significant advantages in terms of energy efficiency. The Airlander 10 requires much less power to stay aloft compared to traditional aircraft. It boasts four 325 horsepower engines, equivalent to about 6 small SUVs. In contrast, a large conventional aircraft like the Boeing 787 requires engines with power equivalent to around 400 SUVs. Vertical thrust, the helicopter element. While buoyancy provides the bulk of the lift, the Airlander 10 also incorporates vertical thrusters similar to those used in helicopters. These thrusters force air downwards, generating an upward force on the aircraft. The addition of vertical thrust serves several purposes. It provides additional lift when needed, such as during takeoff or when carrying heavier loads. It allows for more precise control over the aircraft's altitude and positioning. It enables the Airlander 10 to take off and land vertically, eliminating the need for long runways. This combination of buoyancy and vertical thrust gives the Airlander 10 remarkable flexibility in terms of where it can operate from, opening up possibilities for accessing remote or underdeveloped areas. Aerodynamic lift. Borrowing from airplanes. The final component of the Airlander 10's flight mechanism is aerodynamic lift, the principle that allows airplanes to fly. While we don't fully understand all the intricacies of lift, we know enough to design effective wings and aircraft. The basic requirement for lift is motion. Air must flow over and around a surface, typically a wing, to generate upward force. The shape of the surface and its angle relative to the airflow can significantly affect the amount of lift generated. In the case of the Airlander 10, its entire hull acts as a lifting body. As the airship moves forward, its shape interacts with the air flowing around it, generating additional lift. While this effect is less pronounced than in a traditional airplane, due to the Airlander's slower speed, it still contributes to the overall lifting capacity and efficiency of the aircraft. Advantages and applications. The unique design of the Airlander 10 offers several advantages over traditional aircraft. Fuel efficiency. By relying primarily on buoyancy for lift, the Airlander 10 requires much less fuel to stay aloft. This translates to lower operating costs and reduced environmental impact. Versatility. The modular design of the Airlander 10 allows it to be configured for various missions, from passenger transport to cargo delivery and scientific research. Extended flight time. Some configurations of the Airlander 10 can stay airborne for up to 5 days, making it ideal for long-duration missions or surveillance operations. Minimal infrastructure requirements. Unlike traditional airplanes, the Airlander 10 can take off and land vertically, eliminating the need for long, expensive runways. Payload capacity. While not as high as some dedicated cargo planes, the Airlander 10 can carry up to 10 tons of payload, a significant amount for its fuel consumption. Low emissions. Passenger configurations of the Airlander 10 emit only about 9 g of CO2 per passenger, compared to around 130 g for traditional air travel. These advantages open up a wide range of potential applications. Eco-friendly passenger travel. While slower than jet travel, the Airlander could offer a luxurious, low-emission option for those prioritizing environmental concerns over speed. Cargo transport to remote areas. The ability to land almost anywhere makes the Airlander ideal for delivering supplies to areas with limited infrastructure. Scientific research. Extended flight times and the ability to hover make the Airlander an excellent platform for atmospheric or ecological studies. Surveillance and monitoring. The long endurance and quiet operation of the Airlander could be valuable for border patrol or disaster response missions. Challenges and limitations. Despite its innovative design, the Airlander 10 does face some challenges. Speed. With a top speed of around 25 meters per second, about 90 kilometers per hour or 56 miles per hour, the Airlander is much slower than traditional aircraft. This limits its usefulness for time-sensitive transportation. Weather sensitivity. Like all lighter-than aircraft, the Airlander is more susceptible to strong winds and adverse weather conditions than traditional airplanes. Size. The enormous size of the Airlander, while advantageous in many ways, also presents challenges in terms of storage and ground handling. Public perception. The unconventional appearance of the Airlander, often likened to a flying posterior, may present marketing challenges. Regulatory hurdles. As a new type of aircraft, the Airlander faces the challenge of fitting into existing air traffic control and regulatory frameworks. The future of the Airlander. As of the time of writing, the Airlander 10 has completed 7 test flights, demonstrating its viability as a concept. The company behind the Airlander, Hybrid Air Vehicles, has ambitious plans for the future, including Airlander 50, a larger version capable of carrying up to 50 tons of payload, further expanding the potential applications of the technology. Electric propulsion. Research is ongoing to develop electric propulsion systems for future versions, potentially making the Airlander even more environmentally friendly. Autonomous operation. Like many aerospace companies, Hybrid Air Vehicles is exploring the possibility of autonomous or semi-autonomous operation for future airships. Conclusion. The Airlander 10 represents a fascinating blend of old and new technologies, combining the buoyancy principles of 20th-century airships with modern materials, propulsion systems, and aerodynamic design. While it may look unconventional, the Airlander offers a promising solution to some of the challenges facing the aviation industry, particularly in terms of fuel efficiency and environmental impact. As we face growing concerns about climate change and the need for sustainable transportation options, innovations like the Airlander 10 demonstrate that thinking outside the box, or perhaps, in this case, thinking like a 5-year-old imagining a playcopter blimp, can lead to revolutionary advancements. The success of the Airlander 10 could pave the way for a new era in aviation, where the journey becomes as important as the destination, and where the environmental cost of air travel is significantly reduced. While it may not replace traditional aircraft for all applications, the Airlander and similar hybrid airships could carve out a significant niche in the transportation ecosystem of the future. As we watch this technology develop, it's clear that the Airlander 10 is more than just a novelty or a throwback to the age of Zeppelins. It's a bold step forward, challenging our preconceptions about what air travel can and should be. Whether you see it as a flying bum or a marvel of engineering, there's no denying that the Airlander 10 is pushing the boundaries of aviation and inspiring us to reimagine the future of flight.